Hello, dear students. I welcome you again for this course on Introductory Quantum Mechanics. And this is lecture 4th of our series. And today our lecture is on finite square well potential. Before I start today's lecture, let's remind what we did in our last lecture. In our last lecture, we talked about the infinite potential well problem. We had a potential of the kind that at x is equal to 0 and x is equal to L, the potential is infinite. And a particle is bound inside this potential well. So there was a particle that is bound inside the potential well. And then we applied Schrodinger equation to figure out how this particle will behave. And we found some very interesting results. For example, we found that the particle cannot be at rest. There is at least a minimum energy, which we call as the 0-point energy, which the particle will possess if we apply quantum physics to the particle. Classically speaking, such a result is not possible. Then we also figured out that the probability distribution, that's the probability of finding the particle anywhere in the box, would vary and would depend on in what kind of state it is. So that's what we figured out in our last lecture. Today, our lecture is on finite potential well problem. So this is a very, very important and very interesting so far as the applications of this potential are concerned. Today, what we are going to do is we'll take a problem where the potential is finite and the particle is confined in this problem and in this well, and then we will apply Schrodinger equation and we'll see what results we obtain. This kind of problem has some interesting applications. Recently, the applications have come in what are called as laser diodes. What they do in this laser gallium arsenide light emitting laser is that they engineer the width of the layer between the two substrates such that it forms a kind of a finite potential well, and that there are energy levels that can be controlled. And then the light that is emitted is controlled by selecting the materials and by controlling the width of this layer between the two substrates. So this is a very interesting application of the finite potential well problem. Another very old application is that the nucleus, inside the nucleus, the neutron and the proton energy levels can be, in a very toy model, can be thought to be present in some sort of a potential well. And the gamma rays which emit once there is a transition from one level to another level can be modeled because of this finite potential well problem. So let me actually tell you what the problem is in a little bit of, now give me some description of this problem. Okay, so let me give some description. So you see, a nucleus is a very interesting system, and we have nucleons in the nucleus, fine? And these are many in number. Normally, you know, on average medium mass nuclei, you may have as many as 50 nucleons, right? 50 to 100 is what we have, what we call as medium mass nuclei. Now you see that there are many particles. We have a very difficult problem here because these nucleons, they interact with forces that are not very well understood, and also there are many in number. Suppose we knew the forces with which they interact. We knew them completely. They were as simple as, say, Coulomb force. Even then, solving this problem is almost impossible because of the number of particles that are interacting. What we now do is that we model the nucleus with the help of some potentials. We assume that the nucleons on average experience some sort of an average kind of potential. And if we take a neutron and assume that it is bound by a kind of a finite potential well, whose width and depth are dictated by the experimental results, then we are able to address the levels of the energy that the neutron can occupy inside the nucleus, and that the transition of the nucleon or neutron or proton from one level to another level would give rise to the emission of gamma rays. So this is a very, very interesting application that I thought that I would discuss with you. But anyway, it's only a toy model that you should understand. Fine, so our problem today is to solve Schrodinger equation for such a potential well, so which is finite in depth. So that's what we are going to look for. Okay, so let us start now So this is the kind of potential well I'm talking about. So we have a finite depth potential V naught, right? So let me describe the problem properly. So what do we have here is that the depth of this potential is V naught. Fine. So this is the depth of the potential. So this is depth of the potential is V naught. Fine. So V naught is the depth of the potential. Okay. Then the width of the potential, I have taken 2L, right? These are the parameters that will configure our potential. So 2L is the width of the potential. Why 2L? We could have taken L, but then we will have to take on this side L by 2, and on that, to avoid those fractions, we take 2L as the width, and the X would be from minus L, vary from minus L to plus L. A positive energy state would be above the well. So if the total energy of the particle is positive, then we are outside the well, right? And these are the solutions right now. We are not interested in such solutions. They will represent the scattering solutions. So we are only going to study the bound state solution. So I'll be interested in bound state solutions of the problem. So we are interested only in bound state solutions, means our particle is inside the well, right? So that the total energy of the particle is negative and particle is bound. So what are the different energy levels, and what are the wave functions, what are the probability densities, and those are the problems I'm interested in. Now you can see that there are 3 regions of interest. This is the region 1, right? Then we have region 2, and then we have region 3. In region 1 and 3, we pick the potential to be 0. So we set potential here is 0 in region 1. In region 1, the potential is 0. So in this region, potential is 0. And in region 3 also, the potential is 0. So potential V is 0 in region 1, and it's also 0 in region 3. So that is given by this Vx is equal to 0 for x is greater than L, and Vx is equal to minus V naught for mod of x is less than L. Right. So now we know that we can have some understanding of this potential. Before we actually apply Schrodinger equation, we know there is an uncertainty rule, that there is an uncertainty between the delta x and delta p of the order of h bar, and which will tell us that the uncertainty in the energy of the particle inside the well, and that is of the order of h cross 8m L square. Then if we take the ratio between the depth of the well and this energy, which is the minimum quantum of energy that the particle is supposed to have inside the well, that would give us the strength of the potential. So more this value, more is the strength of the potential. So good so far. So let's go to the next slide. So that's what I told you, that all we need to do is to solve Schrodinger equation for this potential well, which has a depth V naught. Fine. So I'm only interested in this solution, in the bound state solutions. So we're only interested in bound state solutions. Okay. Now we know that the wave function is Vxt is psi of t and phi of t and psi of x. Now we also know that our potential V naught, which we choose to be a constant potential of depth V naught, is independent of time. Since it's independent of time, therefore we need to solve time independent part of the Schrodinger equation. And for time dependent, we already have a solution. So for time dependent part, we already have a solution. The time dependent part is only gives us a phase factor, e to power minus I ET by h bar. So I'll be interested in solving the Schrodinger equation for time independent case, right? So because our potential is time independent, this we learned in our previous lectures. Whenever potential is independent of time, we can break Schrodinger equation into time dependent and time independent part. And then we can solve separately for these two, time dependent and time independent. And since potential is contained in time independent part, so we will try to solve Schrodinger equation here for the time independent case. Now for regions 1 and 2, so this is region 1 and this is region 3. Sorry, for regions 1 and 3, our potential is 0. So we know that potential is 0. Therefore, when V is 0, when we set this equal to 0, so we get minus h cross square by 2m d2 psi x divided by dx square is E psi of x. Just a rearrangement of this equation. You can push 2m upwards and h bar square downward stairs, and then pull them on this side, you get this differential equation. A very, very simple differential equation that we know how to solve. Fine. What we do here now is that in this differential equation, we set this thing equal to minus k square. Why do we, but k is, remember, positive. How it is positive? Because E is negative. Since E is negative, that will set k square to be positive. And also we can figure out the dimensions of k square. You can see here, there is psi x factor here and psi x factor here. So this factor has a dimensions of 1 by x square. And that means this is k square has the dimensions of 1 by L square, which would mean that k has the dimensions of L raised power minus 1. Now, solving this equation is very simple, right? Because this k square, we can write down the auxiliary differential equation, and that will give us the solution for this equation in the form of the exponential functions, right? So let's go ahead. Okay, sorry. Okay, so now we in the first region, so in region 1, so in region 1, we have this as the wave function by solving the differential equation. And then third, we have the similar wave function where we have two solutions, e to power kx and f to power e minus kx. Now we want that, we know that we have learned it that the Schrodinger equation is makes sense only if the wave function is finite, its derivatives are finite and they're continuous. Now we see that when the x will become very large, you see in the third region, when the x will become very large, this will blow up. It will become very, very large, which we don't want. We want psi x to converge. So therefore, this makes no sense, this solution, unless we don't pick e equal to 0, right? Same thing happens to our region 1. In region 1, we see that x is negative. Since x is negative, the e to power kx will converge, whereas e to power minus kx will not converge. That will leave us b equal to 0. So in the first region, we are left with this term only. The solution is psi 1 of x is equal to a e to power kx. And in the region third, we have psi 3 is equal to f e to power minus kx. So we have solved the problem for the region 1 and region 3. And our solutions are very simple solutions. They're exponential in kind. And we have this as positive kx because x is negative here, since x is less than 0 here. So x is less than 0. Therefore, this solution will converge for large x. And here x is greater than 0. Again, this solution will converge for large x, which is important for normalization condition. Now we are interested in the solution of the equation in the region 2. For region 2, we'll solve Schrodinger equation, and we will set v equal to v0 minus v0. Remember, this depth is minus v0. Fine. This depth is minus v0. That's okay. But v0 itself is positive, right? v0 is positive. Depth is minus v0. Minus makes it always negative. Fine. So the v0 by itself is positive. Fine. That you must keep in mind. Now I push it on this side, and this will add with e. E is negative. v0 is positive, but v0 is greater than e. That we have to keep in mind. Fine. So we set k square equal to twice m by h bar square v0 plus e. Fine. So that would make this k square negative, and k would be the imaginary number. And since k is imaginary, again solving for the differential equation, developing an auxiliary equation, we get trigonometric solutions. So in the region 2, we have trigonometric solutions in terms of a new factor that is k prime. So we have k prime defined as 2m by h bar square v0 plus e, some sort of an energy parameter. And then the solution for the Schrodinger equation in region 2 is now c sine of k prime x plus d cos of k prime x. So we have obtained solution for all the three regions. In region 1, we have psi 1 of x is a e to power kx. In region 2, we have psi 3 of, in region 3, we have psi 3 of x f e to power minus kx. In region 2, the solutions are trigonometric functions. Now we need to, from these solutions, they should match at x is equal to minus L and x is equal to plus L. The derivative should also match at those points. That's our requirement. So what now we do is we try to impose the conditions that are must to solve the Schrodinger equation. And these conditions are already understood and discussed in our first lecture, that psi must exist and satisfy the Schrodinger equation. Both psi x and d psi by dx must be continuous, and the derivatives must be finite. They must be single valued, and this important condition that psi should go to 0 as x goes to plus minus infinity if we demand that the wave functions are normalized. So what we do here at this boundary, what we do, we match psi 2 with psi 1 with psi 2. But also, since our potential is even function, the solutions are even and odd. So that would also that would help us in fixing these conditions, because if I define a condition here, if I demand solutions odd and even, that will naturally fix a condition at this point. Okay, so what do I have? I have psi I of minus psi 1 of minus L should be equal to psi 2 of minus L, means these two should match. So if you put x is equal to minus L, it will be a e to power k minus L equal to c sine k prime minus L plus d cos k prime minus L. Similarly, take the derivatives and then match them there. Again, you can match derivatives and functions at x is equal to L as well. So once we do that, so what do we get? We get these equations. So, okay, so we get these equations. So let's clear drawings first. Okay, we get these 4 equations. This one, these two at the first boundary. Okay, and these two at the second boundary. Fine. So these are the 2 conditions that match up at the second boundary. Okay, fine. Now we have even or, because we said that the wave function would be either even or odd. So what we'll do is we'll look for the even parity. Psi of minus x is psi of x. So when we say that, so that would mean that f and a would be same for even functions. Remember, in case of even parity, what we expect is that, suppose this is our potential well, so we expected this kind of solution, right? So you can see the behavior of the wave function is same at the boundaries, right? So therefore, if there is a constant a appended with the wave function, that must be equal to constant f here, because we have a similar solution at this end. So therefore, for a, I can replace it with f, and it is e to power minus kl. And the problem is with this sine term, because sine of minus theta, if you have minus theta, that's equal to minus sine theta. So that will not satisfy this condition. So that's equal to minus sine of theta. Okay, so that's equal to minus sine of theta. So that will not satisfy this condition. That will not satisfy this condition, psi of minus x is psi of x. Therefore, I demand this c for even function is 0. And similarly, for the second case, I demand that now when I take the derivatives and same imposition, since c is 0, so this term will naturally go to 0, and then I have these 2 equations are left. Right, and since these are the 2 equations that define even function, even solutions, right? And now I take their ratio. Now, when I take their ratio, what do I get? I get k in terms of k prime and tan of k prime l. But remember, both k and k prime are positive. Therefore, the k prime l is restricted in values, right? Because we know that tan is positive only between 0 to pi by 2. Fine. So after that, tan would be negative from pi by 2 to pi. And then again, it will take a positive value. So that will restrict the value of k. right? And that would actually guarantee as the quantization of energy. Okay, so let's go to the next slide now. Okay, now since our K square, right? So we explain you in detail. So K square we already set equal to minus twice me by h bar square, and K prime square we set twice me m h bar square, K naught plus E, right? And K is positive, keep that in mind. So K square plus K prime square is twice m V naught by h bar square, fine. So this is when you add these two, just to add these two, fine. You will see that minus twice me by h bar square and plus twice me by h bar square, that will cancel. So we'll be left only with twice me V naught by h bar square. Now we use parameters which are dimensionless. So we introduce Z, which is a dimensionless quantity. If you multiply K prime with L, because K prime is dimensions of 1 by L, K prime L would be dimensionless and we call it Z. And then Z naught, again, L by h bar and root of twice m V naught will be, it will actually give us the strength of the potential is again a dimensionless quantity. And therefore we plug them in this equation by multiplying L square. If I multiply L square here, right, I again multiply L square here, fine. And I again also multiply L square here, fine. So then using these conversion factors Z and Z naught, I get this equation. Z square plus KL whole square equal to Z naught square. This will give me KL in terms of root of Z naught square minus Z square. And since I have solved for even case, at least the relation between the K and K prime was K equal to K prime tan of K prime L. This I got after solving Schrodinger equation. I again multiply L on this side and L on this side and convert them into Z and Z naught factors. So I get this as my final solution. Z tan Z equal to root of Z naught square minus Z square. Remember, it further needs to be solved. And since it's a transcendental equation, therefore solving it is very difficult directly and by analytical methods. The only way to solve this problem is that we have to invoke numerical solutions. So this problem can be solved using computers or numerical methods, what we call. So analytical method for solving this type equation does not exist. But we can get some understanding of the solutions through graphical method. So what we do is that we plot graphs and try to understand what do we get. And also keep it in mind, this was what we obtained for even wave function, right? When we assumed that psi of minus x, when we assumed that psi of minus x is equal to psi of x. This is what we imposed, right? And if we take odd solutions, we'll write psi of minus x is minus psi of x, then we'll get minus z quad z of the same form, right? So that can be done. That can be easily seen. You have to take again those equations and impose this restriction. You will get the other transcendental equation. So now let's try to understand graphically what we get. Okay, this is what we get. If we plot z tan z means the even function. So since we know that it is restricted to positive values only, so you can see that, let me explain you this thing. It's very interesting. So you can see that tan is positive between 0 to pi by 2. And this is the curve for tan z tan z that we get, right? And then this is what we get. This is cot. This is for even wave function, right? This is for even wave function. This we get for odd wave function. Right now we will not consider this. Again, z tan z is again positive between pi and 3 pi by 2. Then again we will have one more solution, which is not one more region where you will get only the odd solution and even solution. So alternately we will have odd and even solutions, right? So then we also plot this root of z naught square minus z square. And since the values are restricted in the positive only, so therefore the curve will be only obtained for this fourth quadrant, right? So this first quadrant, sorry. So we'll restrict our Z0. Z0 is the radius, and the points at which it will cut these solutions Z10, Z represent the energy levels, right? So now you can see that, even if your Z0 is very, very small, say you take it as small as possible, it will still cut the curve at one point. So this is a very interesting result for finite potential well, that there is at least one energy level. Even it does not matter how shallow, say suppose this is my potential well, fine, and I take this V0 very, very small. Doesn't matter how small you take it very, very weak. So this is my V0, the depth of the potential. Even if you take it very weak, very, very weak, there will be at least one energy level. And remember, this kind of analysis helps us to solve deuteron problem in nuclear physics. So that one level system can be understood by modeling it with this kind of potential. Fine. So these are very interesting solutions. And then we can further plot these wave functions and probabilities to get a better feel of what we have obtained. So that comes in the next slide. So let me tell you that. Okay, now if you plot the wave functions, you figure out some interesting cases. You figure out some interesting things. And for example, you see the ground state. Fine. First of all, you can see that the wave function is beyond the walls. So beyond the walls, the wave function exists. Although it exponentially decays, but it does exist there. So this is classically forbidden. So these regions are classically forbidden. Once the particle is in a potential well with energy less than the energy of the well, then there is no point that the particle would be on the other side of the well, classically speaking. But quantum mechanically, it's always having a finite extension over there to the outside world, right? So there is the classically forbidden regions are accessible for the particles in a quantum mechanical well. And then you can see that in the ground state, there are no nodes because the particle doesn't cross you can see there are no nodes. It doesn't cross the zero line, right? But you can see that in the first excited state, there is one node. So as we have second excited state, there are two nodes. So the nodes will continuously increase this minor. For any bound system, it's one of the interesting features of the bound system, the occurrence of the nodes. And then we can plot the probabilities. Again, we can see in the ground state, the probability density is maximum in the middle of the of the well, but in the second excited state, it is minimum there. That's very interesting, right? The particle has more probability to be at L/4 distance, right? And similarly, as the energy goes up and up, a time will reach when the n is very large, that the probability will be flat, the way we expect classically. And then I have here compared the infinite potential well with finite potential well. The dotted one is infinite potential well, and the solid line is the finite potential well. You can see there is an energy difference in the levels, and if you take a limit, as you take limit V0 goes to infinity, then they will merge, right? And infinite square well and finite square well. So they merge when the results of whatever we obtain for finite square well, they will go to infinite square well in the limit when V0 will go to infinity. Okay, so then you'll have the same results. Fine. So this was the discussion we had today. We talked about the applying Schrodinger equation for a finite potential well problem and obtained some very interesting solutions. For example, one of the interesting solutions is that the regions which are classically forbidden are accessible to quantum mechanical particle, even if it is in a well where its energy is less than the barrier in which it's placed. And also we figured out that there is the minimum, at least there is one level. Even if the potential is chosen to be very, very weak, in case of finite potential well problem, you will at least have one level. Right, and then the levels would improve as the value of the potential increases. And then in the limit, when the potential becomes infinite, the values, the levels will be infinite. So that is the end of our today's discussion. And I hope that we made you understood certain interesting features of quantum mechanical systems when they are confined to a constant potential well problem. Thank you very much. In my next lecture, I will discuss about expectation values, operators, finite potential barriers, and also quantum mechanical oscillators. That will be coming up. Maybe it will be covered in 2 to 3 lectures. That depends on how the lectures are planned. So take care and bye.